Hello students, I hope all of you are fine. As corona epidemic is in its peak, so stay at home and stay protected. I hope all of you have seen the previous video on refraction of light, that is the third video of this chapter, and some of you have told me that second law of refraction, that is Snell's law, is not clear. I think you have not started your trigonometry yet, and that's why concept of sin theta cos theta is not there. That's why you found it little bit difficult. Once trigonometry will be done, I think then you can understand the Snell's law clearly. And today I am going to explain lens, its types, image formation by convex and concave lenses, and power of a lens. Now dear students, what is a lens? A lens is a portion of a transparent optical material having one or two spherical surfaces. This is one transparent optical material, and here this surface is spherical but this surface is plane. So this is a lens. If I consider this type of optical material, here you can see both the surfaces are spherical, so this is also a lens. Here all the surfaces are plane. Just because all the surfaces are plane, though it is a transparent optical material, this is not a lens. Now lenses are of two types. One is called converging lens or convex lens, and another one is called diverging lens or concave lens. In case of a convex lens, it is thicker in the middle and thinner at the edges. So if you see this lens, in the central part it is thicker and in the boundary it is thinner. Same with this one. You can see in the central part it is thicker, but in the boundaries it is thinner. Those lenses are called convex lens or converging lens. In case of diverging or concave lens, it is found that it is thinner in the middle part and thicker at the edges. So if you see these edges, it is thicker, and in the central part it is thinner. So if I compare two lenses, in case of a convex lens, central part is thicker and boundaries are thinner, whereas in case of a concave lens, the central part is thinner but the boundaries are thicker. Okay, so what is convex lens and what is concave lens? I think this is now clear. Now let me explain the different types of convex and concave lenses. Depending upon their shapes, a convex lens can be further classified as double convex lens, or it can be also termed as biconvex lens. It can be plano-convex and concavo-convex. In case of double convex, both the surfaces are convex. In case of plano-convex, one surface is plane, another surface is convex, and in case of concavo-convex, one surface is concave and the other side is convex. Now in case of concave lenses, they also can be further classified as double concave or biconcave, plano-concave or convexo-concave. In case of double concave, both the surfaces are concave. In case of plano-concave, one surface is plane. As you can see here, this surface is plane, this surface is concave, and here one surface is convex, another one is concave. Now in this lens, one surface is convex, another surface is plane, so this is a plano-convex lens. If you see this type of lenses where both the surfaces are convex, so this is called double convex. Here if you notice, you will find that in all the cases, central part is thicker as compared to their edges. Here also central part is thicker. In case of a concave lens, you will find that the central part is thinner as compared to their boundaries. In case of a convex lens, the central part will be always thicker as compared to their boundaries, whereas in case of a concave lens, you will find that the central part is thinner as compared to their boundaries. Boundaries are always thicker in case of a concave lens. Now I will discuss some basic terms used in lenses. Suppose this is a convex lens. Considering this surface, I can imagine one sphere, and considering this surface, I can imagine another sphere. Now you can see for this sphere, this is the center, and for the second sphere, this is the center. I have named this one C1 and C2. These 2 points are known as the center of curvature. So here C1 is the first center of curvature, this one is the second center of curvature. Now what is the aperture of the lens? The maximum portion of the spherical surfaces. The maximum portion of the spherical surfaces from which refraction takes place is called the aperture of the lens. In this case, we can consider AB is the aperture of the lens. Now, if we join center of curvatures, that is C1 and C2, by an imaginary line, that line is called principal axis of the lens. Here, C1 is the first center of curvature, C2 is the second center of curvature. So if I join C1 and C2 by a line, those imaginary lines are called principal axis. The point within the lens where a line drawn through the aperture meets the principal axis, that point is called the optical center. In this lens, AB is the aperture, already I told you, and C1, C2, this line is the principal axis, and O is the optical center. Now this is a convex lens and we have considered two parallel rays which are parallel to the principal axis. These rays, after refraction from the lens, they are meeting at a point in the principal axis. That point is called the principal focus of the convex lens. In case of a concave lens, you will find that these rays are parallel to the principal axis. These rays, after refraction, they diverge in such a way as if they are coming from this point in the principal axis. So these points are termed as principal focus. In case of a convex or concave lens, F1 is termed as the first principal focus, whereas F2 is termed as the second principal focus. Since in case of a convex lens, the rays which are parallel to the principal axis, after refraction, they meet at F2. So generally we consider F2 as the principal focus in case of a convex lens, and in case of a concave lens, the rays which are parallel to the principal axis, after refraction, appear to come from F1. So in case of a concave lens, F1 is considered as the principal focus. So in case of a concave lens, F1 is considered as the principal focus, whereas in case of a convex lens, F2 is considered as the principal focus. Any vertical plane which passes through this principal focus and perpendicular to the principal axis, those planes are called focal planes. So a vertical plane passing through this principal focus, this one or this one, which is perpendicular to the principal axis, those planes are called focal plane. Now you can see here, convex lens converges a parallel beam of light. That's why convex lens is also called converging lens. A concave lens diverges parallel rays of light, and these diverged rays appear to come from a particular point. Since a concave lens diverges parallel beam of light, that's why these type of lenses are known as diverging lens. Now I will discuss rules for drawing images in a convex lens. Now this is a convex lens, this is the principal axis, this is the optical center, first principal focus, this is the second principal focus. Suppose this is a ray of light which is traveling parallel to the principal axis. So this ray of light, after passing through the lens, this ray passes through the second principal focus. So any ray of light which is parallel to the principal axis, after refraction, passes to the second principal focus. Okay, now second case, any ray of light which passes to the first principal focus, after refraction, it becomes parallel to the principal axis. Any ray of light which passes to the first principal focus, after refraction through the lens, it will become parallel to the principal axis. And in third case, any ray of light which passes through the optical center will not suffer any refraction and it will go straight without causing any refraction. Okay, any ray of light which passes through the optical center of a convex lens does not suffer any refraction. That means it passes through the lens without any deviation. So let me summarize. Any ray of light which is parallel to the principal axis, after refraction through the lens, it passes through the second principal focus. Any ray of light which passes through the first principal focus, after refraction, this ray will travel parallel to the principal axis. And any ray of light which passes through the optical center, it will go straight without any deviation. In case of a concave lens, any ray which is parallel to the principal axis, after refraction through the lens will diverge as if it is coming from the first principal focus. So we can say a ray of light traveling parallel to the principal axis of a concave lens, after refraction, appears to come from first principal focus. Any ray of light which is moving along the direction of the second principal focus, after refraction travels parallel to the principal axis. Now this ray of light is traveling along the direction of second principal focus. After refraction, this ray of light will become parallel to the principal axis. And third case is similar to the convex lens, that any ray of light which passes through the optical center goes undeviated. That means a ray of light which passes through the optical center of a concave lens does not suffer any refraction, and it passes through the lens without any deviation. These are the rules that we have to follow while drawing images in case of convex and concave lens. Now I'll explain construction of images in convex lens by ray diagrams, and this part is quite similar to the image formation in spherical mirrors. Now in first case, when the object is at infinity such that the rays coming from it are parallel to the principal axis of a convex lens. Now since object is at infinity, then the rays coming from it are always parallel. So these parallel rays which are parallel to the principal axis, after refraction through the lens, we know that any ray which is parallel to the principal axis after refraction through the lens passes through the focus. So this ray will pass to the second principal focus. This ray also after refraction passes to the second principal focus. Since these are the refracted rays and these refracted rays are meeting at f2, so the image of the object which is at infinity will be formed at f2. Since the rays are really meeting, so image is real, and we know real images are always inverted, so image will be inverted. And as you can see, the rays are meeting at a point, the image is very small, so the image is highly diminished. So when the object is at infinity and the rays coming from it are parallel to the principal axis, after refraction through the lens, these rays are going to meet at the second principal focus, so image will be formed at the second principal focus. As the rays are really meeting, so image is real. Real images are always inverted, and as you can see, image is highly diminished and the image is formed at f2, which is the second principal focus on the other side of the lens. And because of this property, a convex lens can be used as a burning glass. In case 2, when the object is at infinity such that the rays coming from it are parallel, but these rays are not parallel to the principal axis. Okay, here object is at infinity and the rays coming from it are parallel, because I told you when the object is at infinity, rays coming from it are always parallel. So these rays are parallel, but these rays are not parallel to the principal axis. In that case, these rays after refraction, they are going to meet in the second focal plane on the other side of the lens. So here as you can see, these rays are meeting at this particular point. And since rays are really meeting, the image will be real. Real images are always inverted, and as you can see, a small dot will be formed. So image is highly diminished and it will form in the second focal plane on the other side of the lens. In case 3, object is beyond 2f1 but not at infinity. Let me show you the image formation in this case. Now from this object, rays are going in different direction. I am considering one ray which is parallel to the principal axis, and we know the rule that any ray which is parallel to the principal axis, after refraction through the lens, it will pass to the second principal focus. So this ray after diffraction will pass through f2. So we can just join this point and f2. Here I am using pen so that you can see it better, but in the exam you have to draw it with a pencil. Another ray which passes through optical center, we know any ray which passes through the optical center, it does not suffer refraction, so this ray will go straight without causing any refraction. Okay, so this ray which is parallel to the principal axis, after refraction it will pass to the second principal focus, and the ray which passes through optical center, it will go straight without causing any refraction. So these two rays, this is one refracted ray, this is another refracted ray, these two rays are meeting here. So that means the image of this object will form here. So we can draw it. This will be the image. As the rays are really meeting, so image is real, and we know real images are always inverted. As you can see, the height of the image is smaller than the object. That means image is diminished and it will form between f2 and 2f2. I hope this case is clear. When object is beyond 2f1 but not at infinity, in that case image will form between f2 and 2f2. It will be real it is inverted, it is diminished, and it will form between f2 and 2f2 on the other side of the lens. The above property of the convex lens is used in photographic camera when a small inverted image of the object is formed on the film which is placed between f2 and 2f2 of the lens. Now in case 4, object is located at 2f1. In that case, one ray which is parallel to the principal axis, after refraction through the lens, it will pass to the second principal focus. Another ray which passes through the optical center, it will go straight without causing any refraction, and these two rays are going to meet at 2f2. So when object is at 2f1, image will be formed at 2f2. Since rays are really meeting, this is one refracted ray, this is another refracted ray, and these two refracted rays are meeting at 2f2, so image is real, it is inverted, and if you see the height of the image and height of the object, it is found that both are same. That means the height of the image is same as that of the object. So when the object is placed at 2f1, then image will be at 2f2, it is real, it is inverted, and it is of the same size, and this case is used in terrestrial telescope. Fifth case, when object is placed between f1 and 2f1, then just see the ray which is parallel to the principal axis, after refraction through the lens, this passes through second principal focus. Another ray which passes through the optical center, it will go straight without causing any refraction, and these two refracted rays are meeting at a point which is beyond 2f2. So when object is between f1 and 2f1, image will be formed beyond 2f2. It is real image because the rays are really meeting, so it must be real. So image is real, it is inverted, and height of the image is more than height of the object, so image is enlarged. So we can say when object is placed between f1 and 2f1, in case of a convex lens, image will form beyond 2f2 on the other side of the lens. It is real, inverted, and enlarged. Now in the sixth case, already I have shown you 5 cases, and slowly we are bringing the object towards the lens. Now object is at f1. When object is at f1, let me show you the image formation. We know any ray which is parallel to the principal axis, this ray which is coming towards the lens, and this ray is parallel to the principal axis, after refraction through the lens, it will pass to the second principal focus, so we can join this point and f2. So this is one refracted ray. And remember that while drawing the images, you have to draw this ray up to the dotted line. Now another ray which passes through the optical center O, we know any ray which passes through the optical center goes undeviated without causing any refraction. As you can see, these rays are almost parallel, which meets only at infinity to form an image. And as these rays are really going to meet somewhere, so the image that will be formed, it will be real, inverted, it will be at infinity, and it will be highly enlarged. Now I'll explain the last image formation in case of convex lens. Here object is between f1 and O. Here this is the object. So we know any ray which is parallel to the principal axis, after refraction through the lens, it will pass to the second principal focus. So this ray will pass through f2. So this ray will go this way. Now another ray which passes through the optical center, it will go straight without causing any refraction. So the ray which is parallel to the principal axis, after refraction through the lens, will pass through the second principal focus, and the ray which passes through the optical center, it will go straight without causing any refraction. And as you can see, these two are diverging rays and they are not going to meet, so we have to produce it in the backward direction. When this divergent beam enters the eye, it appears to come from a point A1, thereby forming the image A1B1. So if this is the object, this will be the image. So when object is placed between F1 and O, image will be formed on the same side of the lens. It is virtual, erect, and it is enlarged. As this figure is very important for exam purpose, let me repeat it. Slowly we are moving the object towards the lens, and now object is between first principal focus and optical center. Here AB is an object located between the optical center O and the first principal focus F1. Now a ray of light which starts from A and moves parallel to the principal axis after refraction through the lens passes to the second principal focus. Another ray of light starting from A on passing through the optical center O passes on undeviated. These two refracted rays give rise to a divergent beam which does not meet on producing forward. However, when this divergent beam enters the eye, it appears to come from a point A1. So A1 is the virtual image of point A. Similarly, B1 will be the virtual image of point B, and so we are going to get one virtual image A1 B1 of the object AB. So when the object is located between F1 and O, image that will be formed, it will be virtual. Virtual images are always erect, so image is erect. It is enlarged as the height of the image is more than height of the object, and the image is formed on the same side as the object. Image is magnified and erect, so lens acts as a simple microscope in this case. Now in case of concave lens, we have to consider two situations. In the first situation, when object is at infinity, and in the second case, when the object is located between infinity and optical center. Now in this case, object is located at infinity. We know the rays coming from an object located at infinity are always parallel, and in this case we have taken rays are parallel to the principal axis. When these parallel rays pass through a concave lens, they get refracted and form a diverging beam. This beam of light on reaching the eye appears to come from point F1, which is the first principal focus of the concave lens, and so a virtual image is formed. So when object is located at infinity, image will be formed at F1. It will be virtual, it will be erect, and it will be highly diminished. Here AB is an object located anywhere between optical center O and infinity. Now from point A ray of light which is parallel to the principal axis, after refraction through the lens, it will diverge as if it is coming from principal focus F1. Another ray of light which passes through optical center, it will go straight without causing any refraction. Now this is one refracted ray, this is another refracted ray. These refracted rays give rise to a divergent beam which does not meet on being produced forward. However, when these two refracted rays enter the eye of the observer, it appears to come from a point A1. So A1 is the virtual image of point A. Similarly, B1 will be the virtual image of point B. So A1 B1 is the virtual image of the object AB. So when object is located anywhere between optical center and infinity, in case of a concave lens, image will be formed between first principal focus, that is F1 and O is the optical center here. So image will be formed between F1 and O. It will be virtual. Virtual images are always erect, so image will be erect. It will be diminished. As you can see, the height of the image is smaller than height of the object, so image is diminished and on the same side of the object. So in concave lens, we have to consider two cases. In first case, when object is located at infinity, and in the second case, object is located anywhere between infinity and optical center. Now I will explain new Cartesian sign convention for lenses. In geometry we have done, in case of a Cartesian plane, this line is called x-axis and this line is called y-axis, and the point where they intersect, that point is called the origin. In this side we consider positive, in the left hand side we consider negative. From origin, anything above is considered to be positive, and from origin, anything below is considered to be negative. Now this concept is used in new Cartesian sign convention for lenses. According to the new Cartesian sign convention, always object is kept in the left hand side, whether it is concave or convex. According to this sign convention, all distances are measured from the optical center of the lens. The distances measured in the direction of incident light are taken as positive, whereas distances measured against the direction of the incident light are taken as negative. The distances measured upwards and perpendicular to the principal axis are taken as positive, whereas distances measured downwards and perpendicular to the principal axis are taken as negative. And these conventions are used both in case of convex and concave lenses. In simple terms, we can say all the distances measured in the right hand side of optical center will be taken as positive. All the distances measured in the left side of the optical center will be considered as negative. All the distances above principal axis like the height of this object will be taken as positive, and the distances measured downwards and perpendicular to the principal axis will be taken as negative. Now in this particular case, AB is the object and A1, B1 is the image. Now AB is the object, that means OB is the object distance. Since it is in the left side of the optical center, so object distance will be negative. We write minus U. Here A1, B1 is the image. So image distance is OB1. Since it is in the right side of the optical center, so it will be positive. We write plus V. Here height of the object which is above principal axis, this will be taken as positive. So we write plus HO. Here A1, B1 is the image which is below principal axis, so it will be negative. We write minus HI. In case of a convex lens, OF2 is considered as the focal length. Since it is in the right side of optical center, so focal length also will be positive. We write plus F. Okay. Since object is in the left side of optical center, object distance will be negative. Since image distance is in the right side of optical center, so it will be considered as positive. Object is above principal axis, so it is positive. Image is below principal axis, it will be negative. And since OF2 is the focal length and it is in the right side of the optical center, so it will be taken as positive. In this figure, AB is the object and A1, B1 is the image. So object distance is OB. Since it is in the left hand side of optical center, it will be considered as negative, so it will be minus U. Here image is A1, B1, so image distance is OB1. Since it is in the left hand side of optical center, so it will be taken as negative. Here AB is the object, so height of the object is AB. Since object is above principal axis, so height of the object will be taken as positive, so it will be plus HO. Here A1, B1 is the height of the image which is above principal axis, so height of the image also will be positive, so it will be plus HI. In case of concave length, we consider this focus, so OF1 is the focal length. Since it is in the left side of the optical center, so this will be taken as negative. A formula which gives a relationship between object distance, image distance and focal length of the lens is called the lens formula. Now the lens formula is 1 by V minus 1 by U equals to 1 by F. In case of mirror formula it was plus, and in case of lens it is minus. So 1 by V minus 1 by U equal to 1 by F, where V is the image distance, U is the object distance and F is the focal length of the lens. Now I'll discuss linear magnification produced by lenses. The ratio between the height of the image produced by a lens to the height of the object is called the linear magnification. So mathematically we write magnification equals to height of the image by height of the object, which is HI by HO. Again, ratio of image distance by object distance is also called magnification. So we can write magnification equals to V by U. So magnification produced in case of a lens can be written as HI by H0 or V by U. In case of virtual and erect images, magnification is positive, whereas in case of real and inverted images, magnification is negative. Now what is power of a lens? Power of lens is a measure of degree of convergence or divergence of light rays incident on it. In simple terms, we can say it is the ability of a lens to bend the rays of light incident on it. Mathematically, we can say the reciprocal of focal length in meters is called power of a lens. So power of a lens is 1 divided by focal length of the lens in meter. In SI unit, power of a lens is diopter. Its symbol is capital letter D. Now, what is 1 diopter? The lens is said to have a power of 1 diopter if its focal length is 1 meter. As the convex lens has a positive focal length, so its power is said to be positive. But in case of a concave lens, the focal length is negative. That's why its power is said to be negative. When a number of lenses of powers P1, P2, P3 are kept in contact, then the net power of these lenses will be P1 plus P2 plus P3 and so on. That's all for today. In the next video, I'm going to explain some numerical problems on mirrors and lenses. Till then, bye bye, take care and wait for the next video.